Okay, good morning or good afternoon, everyone. Welcome to APNIC eLearning web class. This is IPv6 Overview. That's a topic that we are going to cover for the second session of our eLearning day. Now, today is the 1st of April in 2015. It's 1 o'clock in the afternoon from Brisbane in Australia, but it's probably earlier from where you are at the moment. So that's why I keep saying good morning or good afternoon. Anyway, as I've said, this class will be about IPv6 overview. I'll go through the details of what we are going to cover just in a while, but before I do that, I'd like to also introduce myself very briefly. My name is Cheryl Hermoso. I work for APNIC. I'm part of the training team, and we conduct face-to-face workshops, tutorials, trainings, and as well as e-learning type of trainings such as this to the members of the internet community. The topics that we do cover are varied. They're about internet technologies. We cover internet resource management, IPv4, IPv6, network security, DNS and DNSSEC, routing, BGP, IPv6, internet resource management, and all that. So we cover quite a lot of things. So if you're interested in any of those topics as e-learning or as a face-to-face workshop perhaps, if we're in your vicinity, in your area, please check out training.apnic.net for a list of the scheduled trainings that are planned for the next 3 or so months. Okay, so for this class, this is IPv6 overview, and this will run for 1 hour. And at the end of the class, I will be asking you to fill in a survey. This survey is just a very short one that I encourage you to please do because it's important for us to know whether we have achieved something here and whether there are things that we can do to improve this. All right? Because obviously having to do an e-learning type, a remote type of class is difficult. We face a lot of different problems. So if you have any issues with your connection and all that, please let us know when you answer that survey. Now, for this session, I would very much encourage you to participate. If you have anything to add, or not just questions, perhaps you have any additional things to say, please do so. And the way that you can interact with me and the rest of the participants is using the chat panel. Unfortunately, audio and video is not allowed from the participant side. So basically, when you raise your hand, if you see that there's a raise hand on your screens, that means I'm going to transfer the audio to you. So I'm just going to decline that. So if you have questions or anything to add, again, the way to do it, the way to send those data out to us is using the chat panel. All right, so I hope that's clear enough to everyone. And now we are ready to discuss about our topic, which is IP version 6, or simply IPv6. So in this session, we will try to explain to you what exactly is IPv6. So this is an introductory course. This is part of a series. After this, we also have addressing and subnetting, we have transition, we have address planning. But for this particular session, our main focus is to understand the IPv6 protocol. Okay, what are the reasons, what are the motivations behind creating this new protocol? We have IPv4, and why do we need to have IPv6? We will also look at some functional improvements. So when we standardize IPv6, what are the differences between IPv4 and IPv6? What are the improvements that were added on top of that? We will look at different um, functionalities such as the IPv6 extension headers. This is quite new to IPv6, and I think the best way for us to understand V6 really is to do a bit of comparison between V4 and V6. So we will do that a lot over the course of this class. We will have some protocol header comparison, so you see the difference between IPv4 header and IPv6 headers. And lastly, just very quickly, IPv6 address distribution. So once you understand what is IPv6 and you might be interested to get your own IPv6 blocks, how do we go about getting those IP addresses, right? So that's the plan. If you have anything that is maybe beyond this that you want to ask, please do so. We'll try as much as possible to still answer them in the limited time that we have. Okay, so let's begin with a brief overview of IPv6. So basically, you already know what an IP is. Coming into the class, I'm hoping that you know what's IPv4. Basically, the main protocol behind is IP, Internet Protocol, which is part of the TCP/IP protocol stack, which is essentially your layer 3, the one that is in charge of logical addresses. So in that level, okay, in that layer, you get logical addresses, IP addresses, source address, and destination address. So that's your IP, right? It's one of the main pillars to support the internet today. Okay, we want your computers, your laptops, your machines, your mobile phones to be accessible to the internet. And how does that happen? We assign an IP address. More specifically, we assign a global IP address, globally accessible IP address. Now, the current version of IP protocol is IP version 4, and the version that we are introducing here is IP version 6. It says there that it is new, but I'm kind of worried of saying that IPv6 is a new protocol because actually it is not. If you look, I probably have some um, um, outline of how it evolved in the next few slides, but you will see that IPv6, it's not exactly a new protocol. It's been there for a while, but the reason that we are jumping into it now is because of a specific problem in IPv4, which is its limitations. We are reaching its limitations. So that's IP version 6. Okay, that's the new protocol that we are encouraging people, networks, to use. Now, I get a lot of questions about the difference between V4 and V6, which we'll go through. And another question that I get a lot is about the jump from V4 to V6. How come from IPv4, why are we jumping straight to IPv6? Where is IPv5? So maybe it's just a curious question, but actually there is IPv5. It's Internet Stream Protocol. It is an experimental protocol, so it's not exactly standardized. You won't see that implemented in your equipment and all that. But it was an experimental protocol with RFC 1190. Now, in most of the materials that you probably will be reading, if you want to learn more about IPv6, in the early days, you probably won't see IPv6 in those documentations, in those RFCs. In the early days, IPv6 was called IPNG, or the IP next generation. So they're basically seeking for a next generation of IP that will eventually replace IPv4. So in its development stage, we called IPv6 as IPNG, or IP next generation. Right. So a bit of an overview or a background of how it came to be. As I've said earlier, with IPv6, your main goal is to implement IPv6 as an maybe not exactly a replacement nowadays. It's mostly just to complement because you want to implement IPv6 on top of IPv4. So you have two of these protocols running. But how did we come about it? So if you will see in the early days of the internet, which started out in late 1970s, but gathered a lot of attention and mainstream access in the late 1980s to early 1990s, you see there that in around, I'm trying to use the pointer, let me just, oh, there you go. Okay, in the early days, in still around 1990s, there was a first wake-up call by a guy named Solensky in one of the IETF meetings about the possible IPv4 address exhaustion. What does that mean? So IPv4, IP version 4, consists generally or ideally of 4.3 billion addresses, right? Because that's 32 bits and it's exponential. So 2 raised to 32 is about 4.3 billion. So ideally, you can have about 4.3 billion machines that you can assign an IP address. But that is huge. If you look at it in the 1980s, where most of your equipment, most of your machines are these big servers, that not everyone owns a machine or a computer, then it's kind of impossible to think that we will be able to use all those 4.3 billion. But in 1990s, when it has started to become more mainstream, people want to use it, people want to connect to the internet, then they pointed out that there is a possibility that it will be exhausted. We will run out at some point. And during that time, we are using what we call as classful addressing. Class A, Class B, and Class C. So with classful addressing, if you need an IP address, what you basically do is go to one of the guys in ARPANET, and then tell them that, hey, I need an IP address, give me a slash 24 or give me a class A, right? A class A is very big. It's equivalent to a slash 8 in CIDR nomenclature that we use now. So it's very big, but not all of it is being used. So that's how wasteful, if you look at it from our perspective now, that kind of IP address distribution is very much wasteful. If you are going to assign that onto, let's say, 500 computers, and you have a class A, which is about can be used for about more than a million hosts, then that is very much wasteful. So they saw that with this limited resource, by around 1996, 1997, something like that, we will have run out of IP address. And so from that point on forward, they have started looking at possibilities of addressing this issue. In 1994, they formed a group or an area called IPNG that looks at this effort. They listed down some of the possible options that can be used. They looked at different proposals that can address the issue. So basically, what they thought is to create a new protocol, okay, to have a new protocol that will replace IPv4. And those different proposals have different specifications. Some of them said that we should use 128 bits. Some of them said just use 64 bits. Some of them had all these extra functionalities that are added. Some said that we should use a flexible size of number of bits. Okay, but eventually, in the version that we are using now and the standard that we are using now, IP version 6 uses 128 bits of address, and that is from a proposal done in 1995. Okay, the first version of the IPv6 address specification, which is RFC 1883, was published in 1995, and then 3 years later on, RFC 2460 came to be, which is the current standard that we are using, okay, as the IPv6 specification. So you see why I'm worried about saying that IPv6 is new. It's because as early as the 1990s, we already have the IPv6 specification. IPv6 is already a standard. However, adoption rates from 1990s until about 5 years ago have been very, very minimal. And that the main reason is because we still have IPv4. And IPv4, the networks that we have, the internet that we have is very stable. Given that we're using IPv4, there's no problem with it. Why do we have to replace it? Now, the problem is IPv4 is getting exhausted. We are running out of IP addresses. If you look at this graph, you notice there that those are the lines there with different colors are the different regional internet registries or RIRs. Each of these RIRs are given an IP address block from IANA, the Internet Assigned Numbers Authority, and from there they distribute that to their customers or to the local internet registries. If you notice, these are projections up to when the IP v4 slash the last slash 8 block will run out. So in APNIC region, in our region, we actually have already started distributing from the final slash 8 in in about second quarter of 2011. So right now we are about 80% still available out of that final /8. And the problem is, like, once we run out of that, there is there's no more IPv4 pool. And the more problem that we get there is, what if we want the internet to grow? Okay, we have our stable IPv4 internet nowadays. That's fine. It's running, people are connected, people are getting their information that they want, they're getting the services that they want. The problem is, the internet is also a growing ecosystem. You have different machines connecting to it every day, different networks connecting to it every day. You have different um, equipment or mobile or different gadgets that you want to connect to the internet. And with that idea in mind, there is no way that the internet will grow because we are facing running out of IP address, right? So that's a main dilemma, and so we needed IPv6 to address that. Why? IPv6 provides us with plenty of IP addresses. So I'll have a look. We will have a look at the IPv6 address text representation later on. But before, with IPv4, we have 2 raised to 32 number of addressable devices. That's 4.3 billion, right? Devices that you can have an IP address. Now with IPv6, we're using 128 bits. If you just look at the number of bits, IPv4 is 32, IPv6 is 128. IPv6 number of bits is 4 times bigger than IPv4. And when you look at the entire address pool, it's not just 4 times bigger. It's actually, since it's exponential, that's 2 raised to 128, which is about 3.4 billion addresses. So you have plenty of address space, which we can now use to assign to all the gadgets that have been sprouting these days. The difference with the internet nowadays is that we are into Internet of Things. We don't just have one desktop for each person. We actually have one desktop, one mobile phone, one tablet. Our home equipment probably will have their own IP addresses. Our phones, our cars, basically everything, every electronic gadget can probably have its own IP address. So with IPv6, we can address those growing issues, right? Another is they're looking at IPv6 to become a solution for a very complex hierarchical addressing need. So if you look at how we are distributing IPv4 addresses, it's kind of convoluted in a way that it's very difficult to aggregate all of them. So the idea, which is not exactly implemented nowadays, is that IPv6 will address this issue. So it's more hierarchical, so it's easy to aggregate all your IP address blocks. IPv6 provides us with end-to-end communication. Now, with IPv4, we have different types of addresses, right? We have a global address or a public address. We have a private address. Now, the reason we have private addresses, or we're using private addresses mostly in LANs or in our local networks, is because we don't have enough public addresses to use, right? We probably have a /24 assigned to our entire organization, but we have thousands of computers inside. So we use private address. And from that private address, we make that available to the internet using NAT. So we're using NATing, or network address translations. Now with IPv6, we are not going, the idea is not to use NATs. All your equipment should have accessible, it should have its own IPv6 address, and should have end-to-end communication with all other hosts on the internet. And if you use NAT, you're probably aware of all the repercussions, the problems that are associated with it. Things like if you're using VoIP, you have problems going through a NAT and things like that, right? As well as some security issues that goes along with it. Now, another motivation behind IPv6 is to be able to ensure security and reliability of data and faster processing of protocol overhead. So the idea behind this is that IPv6 should be faster. Why? Because when you look later on at the headers are actually simplified over IPv4. So the things that you use because we have learned a lot by using IPv4 for about possibly 1 decade before they finalized the standard for IPv6. So from that, they have learned a few things about how routing works, what are the important parameters and all that, and so they have applied some of that into IPv6. Okay, and stable service for mobile networks. There is such a thing as implementing IPv6 in mobile environments, which is gaining a lot of popularity these days. And so this comes in very useful for that scenarios. So by this point, you should all know the main reason why we have IPv6, and that is because of the address exhaustion of IPv4. We are running out of IPv4. It doesn't mean to say that we don't have IPv4 anymore, because when you come to an RIR, when you come to APNIC, obviously we can still provide you with an IPv4 address space. Okay, but the problem is the supply, given the demand, the growing demand of um, internet connected devices, there is a very short supply, and sooner or later, because this is a limited supply, we will run out of IPv4 address. Okay, and IPv6 is a good replacement for that because mainly of the larger address space that it has. I've already mentioned the addressable size earlier. With IPv4, it's 32 bits. With IPv6, it's 128 bits. So the equivalent possible addressable devices ideally would be about 3.4 times 10 to the 38. That's way, way bigger than IPv4, right? Now, another thing which we will be looking at in the next slide is, all right, we know why we want IPv6, but since we are coming up with this new protocol, might as well learn from IPv4 and add some functionality, some new things, some um, improvements over IPv4. So that was the idea behind this. So the current IPv6 protocol has these functional improvements. We are already aware about address space, of course, from 32 to 128. Another thing is the use of stateless auto address configuration, or what we call as SLAC, S-L-A-C. This means that you don't have to configure IP address for your hosts anymore. You don't need a third-party DHCP server to assign IP addresses to give you an IP address lease, but your machine can have its own IP address by the moment you turn on or enable IPv6. Isn't that a good thing? With IPv4, what you do is, well, of course, if you have a machine, you just turn it on, you connected it to the network. One is you either assign the IP address manually. The other way is to let it go and check with the DHCP server and get an IP address lease. So those are the two things that are possible. Now, SLAC was developed around the same time that DHCP was being developed, so you see some similarities between them. But basically with SLAC, you don't need an external device, an external server for you to provide you with an IP address. There is a range, okay, a link local address. That block is used for stateless auto address configuration. So basically you'll have an IP address, and this machine will now be accessible via v6 onto the local link. Okay, not beyond routers, but just within your local network. Okay, next one is about performance, which we will be looking at more closely later on. With IPv6, we are using a fixed header size of 40 bytes. With IPv4, we use 20 bytes, but that is the minimum. It usually increases more than that depending on the additional options and parameters in your IP header. But with IPv6, we are using a fixed header size of 40 bytes. It's 64-bit header line, which in the early days was very useful because we have either 32 or 64 bits. Nowadays, most processors, most machines are already just using 64 bits, so not much difference anyway. Next is hop-by-hop segmentation. So what does that mean? There is such a thing as path MTU discovery in IPv6. Now, what happens if you have a packet? You have a packet that wants to traverse from A to D, okay? So from A to D, maybe it has to go through different routers. So it will hop from A to B, B to C, C to D. Now, the problem there is some of these links have limitations. Maybe I only allow this much bandwidth. Okay, I only allow, we call that in this term as MTU, or the maximum transmission unit. The MTU size that's allowed for this link is only this much. And so if I have something that is bigger, what happens is it will be dropped and I have to reform my packet again and then resend it to the same link. So that's what happens. So if you have a packet that goes from A to D and then somewhere between B and C, the link doesn't allow an MTU size of 1500, maybe it only allows 1200, then I'll have to redo my packets and then resend it again, which adds to the latency. With IPv6, this is a good implementation because even before you send a packet, you already know the MTU size of the link. Okay, so it uses ICMP, or you know ICMP as when you're doing ping, right? So ICMP v6 is used to find out the MTU size of the links, and so when you send the packet, it's ready, no need for retransmission later on. So that's path MTU discovery. Other things, other functional improvements that have been added is built-in features for multicast. And related to that, somewhere down the bottom here, you'll see no more broadcast. So normally when I teach this course, people get confused or are surprised. How come we're no longer using broadcast? And broadcast is very useful in IPv4, right? If you're trying to find out the machines in your local network, maybe you're using ARP, you usually would use broadcast. So it's used in a lot of protocols. Now, with IPv6, we no longer use broadcast, okay? Instead, we mainly use multicast, okay? And well, we also use anycast, but mostly multicast to address a smaller group, not the entire network. So that's the main difference between v4 and v6. Okay, we also have mobile IP, which is about implementing IPv6 in the mobile environment. In this scenario, we won't go through in the details because there's a lot of things happening in here. But essentially, with in IPv4, to be able to send messages in mobile, you do triangular routing. With IPv6, we don't do triangular routing anymore, so somehow it's a simplified implementation if done properly. Another thing, we always say that IPv6 is secure. Okay, I always get people marketing IPv6 as a secure alternative to IPv4. Well, there is some truth to that. Of course, you still need to add more security, not just on your IP layer. But the reason behind that is because IPv6, it can implement IPsec by default. IPsec, by the way, is IP security. We have IPsec in IPv4, but originally when IPsec was being developed, it was for the purposes of being added as part of the IPv6 protocol. So in IPv4 now, we have your IPv4 protocol, and then on top of that, alongside that, you implement IPsec. But with IPv6, IPsec is a built-in component, a built-in part of the IPv6 protocol. All right, and you can enable that at any time. It has built-in support for QoS tagging, therefore faster processing, less latency and all that, better quality of service, and no more broadcast as we have already discussed before. So those are just some of the things that were added, more functionalities that were added on top of IPv6 as when it addresses issues with IPv4, when it was implemented as a new standard. Any questions so far from everyone? Okay, so we're halfway through the scheduled time actually, but I don't think we're halfway through the slides. So I'm gonna speed up a little bit from here on. But if you have any questions, please feel free to write them down on the chat or raise them at any point during the discussion. All right, next thing, something that is quite new to IPv6 is what we call as extension headers. Now, remember, we talked about the size of the IPv4 and IPv6 header. With IPv6, it's 40 bytes. With IPv4, it's 20 bytes, but it's not fixed. In IPv6, the reason it's fixed is because we only added the essential parts. If you need more things there, we will add it as an extension header, right? So an extension header is optional, okay? It makes two things. One is removes all the unnecessary part or optional parts from the main IPv6 header. Another is it makes it possible because IPv6 is still an improving protocol. It makes it easy to add new features to the IPv6 protocol later on. Okay, the number of extensions are not fixed. The total length of the extension header becomes a chain, so it changes its variable. And the extension header is usually placed between your main header and your payload. So in your packet, you have an IP header and an IP payload. Now, if you want to add an extension header, this is inserted somewhere in between your IPv6 header and your main IP payload. What does it look like? Let me just skip that for a little bit. This is an example, right? So if you look at this diagram here, you have your typical IP header and your typical IP payload. Your IP payload is obviously consisting of your TCP data from the upper levels, upper layers. So you have your TCP header and your TCP segment. So what if you have an extension header? Technically, if you don't have any extension headers, in your main IP header, it also has a next header field. In the next header field, it shows you that this is the value of the next header. So basically, you're telling the, you're basically saying here that from here, what will be the extension header that follows? Or is there even an extension header to begin with? So going back to the previous slide here, these are the codes for the different next header fields. So 0 is hop-by-hop options, 2 is ICMP, 6 and 17 are TCP and UDP. For implementing IPsec, you have 50 for ESP, AH is 51, etc. 60 is a destination option. You have source routing, that's 43. If you have fragmentation, that's 44. So basically, there are different codes for different next headers. Now, if what follows is a TCP header, okay, where is TCP here? TCP is 6. So notice that here, your next header value and here will have a value of 6. Meaning it says that there is no extension header. What follows is the TCP data, right? Now, what if there are extension headers? And as I've said, it becomes like a linked list. You add more extension headers in between. You just need to specify that the next header that follows this header or this extension header is this type, okay? And then at the very last one, if what follows is a TCP header, just make sure that that next header shows 6, the code for TCP. So notice in this example, you have IP header, next header is 0. 0 is your hop-by-hop options. In your hop-by-hop options extension header, the next header pointed to is 44, which is your fragment header. And then from your fragment header, it points to your TCP header. Okay, so there is a tendency for your entire IP packet to grow big because of this. You can add as much extension headers as you want in here, right? So this is something new. Perhaps if you haven't heard of IPv6 before and this is the first time, then this is a very new feature for you. Okay. Now, what about fragmentation? How does IPv6 handle fragmentation? It's kind of varies where it's like your routers handle fragmentation. When you talk about IPv4, it's kind of very different, and it is dependent very much on how routers would do it. In IPv6, we kind of try not to have fragmentation. Okay, remember our discussion on path MTU discovery earlier on. This is how we avoid using fragmentation. That is because beforehand, even before we send out the packets, we are already aware, or we already know the optimum size, the maximum MTU size that we can then use to create or form our packets before sending it out. Okay, and that is done using a discovery process. So path MTU discovery, which is part of ICMP. So ICMP packets are sent through. Um, and then it will reply if the device receives an ICMP packet that's too big, meaning that you have to make that a smaller one, meaning the MTU size is smaller than what you have initially set your device to use. Okay, so that's basically some details of how fragmentation and path MTU discovery is used. These are the basic defaults for MTU size for V4 and V6. Okay, for IPv4, that's 68 octets, 1280 octets for IPv6. But the typical one that's assigned onto your machines, onto your routers, are 576 for IPv4 and 1500 for IPv6. Just remember that. So normally you set your you just leave it as a default, and that's 1500 MTU size, and then you can change it. You can set it to a higher or lower value of your MTU size. We've talked a little bit about IPsec earlier on. As I've said, IPsec is developed to become part of IPv6. So IPsec is a mandatory part of IPv6 protocol. So with this, meaning you can have end-to-end connectivity, okay, using the IPsec protocol between different machines onto the network, or even between different routers or different networks as well. So that's how IPv6 provides security for its implementation. Any questions so far? All right. Here I'd like to concentrate a little bit on the main differences between IPv4 and IPv6 by looking at its header. Okay, so on your left you have your IPv4 header, on your right is your IPv6 header. So what do you first notice? So there's a color coding scheme there, there's a legend somewhere at the bottom you'll see here. On the left, IPv4, it's kind of, there's a lot of things going on there. You have a lot of fields, they have many different purposes. And with IPv6, we have simplified a lot of that. With IPv4, what are the different fields? The ones in yellow are fields that have been kept from v4 to v6. So you notice you still have those fields from v4 to v6. You have version. Version in v4 just contains 0100 for 4. In IPv6, the version will have or will contain the binary equivalent of 6. The source and destination addresses are still there. Main difference basically is the size of this field. In IPv4, that's 32 for each source and destination. With IPv6, that's 128 bits for each source and destination, right? So they're the same. They remain the same. Now, the red ones here, mostly on the left on your IPv4, are fields that have not been kept in IPv6, meaning we remove them. So even if you don't remove them altogether, they are added into the extension. Why do we do that? Either they're not very important in the IPv6 implementation, or they are optional fields. Most of them, even if it's not required, since they have dedicated fields there, they will probably only have default values, like maybe all zeros, which your router, your networking equipment still have to parse or still have to try and understand, right, and interpret. Now, if you remove them, then you remove that burden on your router to actually try to understand the contents of these fields. And you only add them when necessary, when you need it. So you add it onto the extension headers rather than by default adding it to the main header. So things like identification, flags, fragmentation offsets, and the option field, which makes the IPv4 header variables in size, we remove them. So by doing this, by removing most of these fields, we make the IPv6 header fixed size, right? Now, what other fields do we have? The one in bluish green color is our fields with names and positions change in IPv6. So minor changes, but most of the functionalities are still very similar. In IPv4, we have type of service that is called traffic class in IPv6. In IPv4, you have total length. Now, in IPv6, we don't need to always know the total length because we know that the IPv6 header is fixed size. So we only have to know the size of the payload. So a bit of change there. So the contents of this field is only the size of your payload, not the entire packet. Okay. What else? You have the time to live. Time to live in IPv4 is replaced by hop limits. Why do we have this? Well, time to live, or TTL. Okay, you're all familiar with this. It is based on time. And from one router to another router, one machine to another machine, there are minute differences between these timing values. Even if, let's say, they're connected to the same um, NTP servers and all that, there will still be minute differences between them. So we want to try to eliminate those minor differences. So instead of using time as a value of the of your packet's lifetime, we use hop limits. So with hop limits, I think that's 8 bits. So you have 2 raised to 8, so it's 255 hops before this packet will be dropped because it didn't reach its destination. So we are basing it on the number of hops between routers to routers until it reached its destination point, right? What else? I think I've mentioned most of them. Protocol, next header over there. Next header, you already know what it does. I've shown you earlier. It's used for extension headers. And the last one is the dark blue one is new field that is introduced in IPv6. That is flow label. So flow label is kind of similar to traffic class, or in IPv4 terms to type of service. So in TOS or traffic class, we have a set of like parameters or labeling for different types or different classes of packets, and we give priority to that accordingly. Now with flow label, it just gives you more granularity. You can define a certain flow, okay? So maybe you want to prioritize this type of traffic. Maybe you want to prioritize voice over data. Maybe you want to prioritize streaming data over other forms of information, other forms of packets. Then you can do that. You define a flow and you give proper QoS, proper priorities given that. All right? So just to wrap up this slide, basically you saw the difference between V4 and V6, how we made IPv6 a lot simpler than IPv4. IPv4 here contains about 10 basic header fields. In IPv6, it's much less. It's only about 6. The size of your IPv4 and IPv6 are very different. Your IPv6 header is double the size, but it's fixed. With IPv4, it's only 20 bytes, but it's variable. So basically, this makes it easier for your routers to deal with all the incoming packets and send them, work on it accordingly. So less latency, faster processing, better performance by most of the routers. Right? Any questions in this? No questions? All right, that's good. All right, now in the next few slides, I think I'm just going to go through the actual IPv6 addresses. So here you'll see the entire IPv6 address space. It's this whole gray thing, gray circle, gray donut over there. Now, there are different types of IPv6 addresses, and you will learn about that more if you attend another session, another module called IPv6 addressing and subnetting, where we'll take a closer look at this. But I don't want you to get out of this class knowing what IPv6 is, but not actually understanding when you see an actual IPv6 address. So as I've said, there are different types of IPv6 address, similar to how we have different types of V4 addresses. We have public and private addresses in V4. In that sense, we also have global addresses, which are kind of equivalent to public addresses. We also have sort of private IPv6 addresses. So there are different types that falls under that. You have link local address, site local address, um, um, and and all that. But here you have the global address, the global unicast address, and that's usually um, like a chunk of that is already within IANA. Okay, IANA is the Internet Assigned Numbers Authority. They maintain the pool of IPv6 and IPv4 addresses. So when it comes to IPv6, it contains a /3 IPv6 block in its pool. We call this as the global unicast address. This is the block that is distributed to the RIRs and then later on distributed to the users, to end hosts, to LIRs. Now what you can see here is that from that block that IANA has, this is only a /3. And if you look at it, how big that is for the entire IPv6 space, that's only 1/8 of the entire IPv6 address space. Okay, and from that /3, we have subdivided that into /12s. So I hope you know a little bit about IPv4 subnetting. Nothing much different between them, but essentially we are subdividing that /3 chunk into different /12s. From that, you can say that you have 512 /12s in a /3. Okay, and from those /12s, we have distributed /12s to each of the RIRs. So 5 of them have been given to the 5 RIRs. In our region, we have 2400/12. And then there is one /12 that has been used for experimental purposes, basically for other purposes that is not included to the ones that are being distributed to you. So if you come to APNIC and request for your IP address, for your IPv6 address, most likely you will get a block that will start with 2400/32. All right, and that's mainly because of this. Now, what does this tell us? At the very beginning, I told you about the main consideration of using IPv6, and that is a bigger address space. And by looking at this diagram, you'll see what I mean. It's very huge. We have /12s assigned to each of the RIR. Okay, and if we run out of that /12, okay, we can always go back to IANA, request for another /12. Remember, there are still about 506 /12s that is reserved within IANA. That is a lot, right? And what if, just what if in the next 10 years, okay, we use IPv6, we go to the RIRs, request for blocks, so these RIRs go to the IANA, request for the /12s. What if IANA have now distributed all the 512 /12s into all the RIRs? That means, okay, we've used up this /3 chunk. Okay, and once we've reached that point, there are still about 7 /3s in the entire IPv6 space. So that only shows us how big an IPv6 address space actually is. So I hope that gives you more qualitative idea of the size or the how big the IPv6 address space is. All right, so any questions from the class? If not, here is just some idea about how you can get your IPv6 address. If you don't have IPv6 address yet and are thinking of implementing that, this is perfect time to do it. This is a good time. Maybe you're not looking at actually making that into production yet, but do set up an experimental environment where you can implement or you can run both IPv4 and IPv6. One thing that you have to understand, by the way, with IPv6 is that it is not compatible with IPv4. Maybe I may not have mentioned that earlier, but it will be important once you think of transitioning into IPv6. Basically, what you have now are two separate kind of internets. So you have the IPv4 internet and you have the IPv6 internet. When you have the IPv4 internet, those that are running IPv6 and IPv6 only are not reachable via v4. And those that are in the IPv6 network cannot access websites, services, machines that are using IPv4. That's why we have transition. We have a way of making them interconnect or still be able to communicate with each other. But essentially, that's the main difference. That's why if you're going to implement IPv6, at this point, the best way is to do dual stack, where you have both IPv4 and IPv6 running in your network. All right. So basically, that's a bit going forward if you're an advanced user. But right now, the best thing is to get your IPv6 addresses. And if you are already an APNIC member and you have your IPv4 address, it's very easy. If you are already a member, log into your My APNIC account, and I think just in the landing page, you can claim your IPv6 address. That depends on what type of delegation you have for v4. If you have an assignment, IPv4 assignment, you get a /48 IPv6. If you have an IPv4 allocation, you get a /32 IPv6 address. All right, so those are the sizes of IPv6, and that's already very big. Okay, if you're new to APNIC, if you want to apply for resources, you can do the membership, IPv4 address application, and IPv6 address request all at the same time. All right. Okay, so I think yeah, we're just about winding down the session. This is a graph of the BGP routing table for IPv6. I'm not sure how many of you are into routing in the class, but if you notice with IPv4, there is about, I think, close to 50,000 prefixes that are announced on the global routing table. And this kind of gives you an idea of the size of the internet itself. With IPv6, you notice that it's not really as big as IPv4 just yet. Okay, but over the past 3 or 4 years, you see a very steep change or increase in the routing table size compared to how it was in the early 2000s. So around 2009, 2010, 2011 here, this is a time that we have faced the exhaustion. This is the time that we have given the final /8 blocks to all the 5 RIRs. And this is the time that we have started changing some of the policies when distributing, okay, from that final /8. Nowadays, if you come to APNIC and IPv4, you get a /22 max from the final /8, right? So that's not enough for most people, most new entrants into the internet business. Okay, if you're starting up an ISP, can you are you okay with just a /24 public addresses? Probably not. It will probably last you a year or so, but after that, how can your network grow or keep on growing? That's why you have IPv6. IPv6 makes that possible. Okay, and sooner or later, once we have more services running on IPv6, which right now we already have a good number. Most of the CDNs, most of the big providers are making their services available in v4 and v6. So that made way for this very big growth or increase in the IPv6 routing table size. All right, so I hope that after this, you at least have gained some knowledge of IPv6, and it will help you to further investigate your options as an organization, as a company, to implement IPv6 in your infrastructure. I'll be very happy, or most of us here at APNIC will be very happy to help you out. If you're stuck with anything, please maybe send us an email or nudge us or look at our previous presentations or other people's experiences as well to help you implement IPv6. All right, so I think that's the end of this session. Yes, very much. So if you have any questions, this is the time to write them down on the chat. Otherwise, the feedback form is here. Can you please fill in this feedback form for me? It will take about a couple of minutes, but that's it. And then you can get a copy of the slides after that. But I'll be more interested to answer your questions. If you have any, please write them down on the chat. Maybe not questions, maybe just observations or anything that you wish to add for other participants. We still have about 4 minutes to go, so type in your questions. All right, that's the link to the survey. I just put that in there just in case you can't click onto that link on the slides. And this is the link to the FTP. All right, a question from TOKS. When is the session for subnetting? Okay, I'll have a look. You can also have a look yourselves. Go to training.apnic.net/events and you'll see all the scheduled e-learning there. Today we're doing IPv6 overview. It's the 1st of April. Next week, April 8th, we will have IPv6 addressing and subnetting, and that is at, just wait while it's loading. It's at 1 o'clock. So that's also the second session for next week. So if you can join us for that session, that will be very good. If you can't wait for that to happen and you want to quickly go through while what we've discussed is still fresh in your minds, you can also check out our YouTube channel. So that's youtube.com/APNIC training. And you have there a recording or some recordings of our previous e-learning sessions. So it's there, youtube.com/APNIC training, and then view them at your own pace or at your own free time. Okay, so any other questions? If not, I won't hold you much further. Thank you very much, everyone, for your time and for your attention. I very much enjoyed this session with you. I hope you learned something. I think you did, but hopefully that's not the end of it. Please go through the other materials as well and start deploying IPv6. Okay, with that, thank you very much, and so see you another time. Bye-bye.